Okay, so believe it or not, you actually know all the theory there is to know about 2D motion. And now all that's left to do is to actually see how that works in practice. Okay, all right, so let's immediately look at an example, right? So finally, it's a slightly less violent example. A ball is thrown horizontally from the top of a cliff. All right, so horizontally, you throw a ball and it hits the ground below 3 seconds later. Okay, so note that we are given in 2 significant figures just for the final answer's sake, and it's asking how high is the cliff. Okay, all right, so let's give that a try. All these type of problems, you want to first start with a diagram. So always start with drawing a diagram, and remember, when you draw a diagram, you want to state your coordinate system. All right, your system or your coordinates. So later on, you can actually describe directions or angles and stuff like that, and also the origin. All right. So yeah, it's important to see are things positive or negative and stuff like that, and also the origin. All right. So let's see. So you have a cliff. You're throwing a ball horizontally. All right. So this is your initial velocity. So it will probably fall along a path like this, and we know that it takes 3 seconds like this. And usually when I label something, label all the information on here. If it is in SI units, I will suppress the units. It's always easier that way. Okay. If it's not in SI units, I always convert it 90% of the time. I convert it into from the non-SI units to SI units first, which means meters and seconds and kilograms, sometimes called the MKS system, right? So these are the standard base units of SI units. And once you do that, the benefit is if everything is in SI units in your equations, you don't need to write any units until the very end. You just put it back in. That's usually the safest and quickest way. It's not only the quickest, it's also the safest way of doing these things. Okay, right. Anyway, so and also don't worry about significant figures in the diagram, just to keep things. The simpler it is to see and interpret, the better. Right. So that's little tips on how to solve these problems as well as I go along. Right, so that's the initial velocity, right? What I need to put in the coordinate system. So let me be traditional. I will use XY this way, all right? Because I want to show you how the minus signs and stuff goes in this way. So when unsure, just stick with this. But sometimes if you know what you're doing, you can flip this around. If, for example, if the ball is drawn that way, it might be more reasonable to put X the way. But you should always get the same answer that way. Okay, so that's the diagram. And then now you want to write out your givens and the aim. Okay, so state your given and the aim. So what we're going to do, instead of just write out the suvat variables in the X direction, you want to duplicate this like this. Okay, and then put X's everywhere here and Y's everywhere except for the time. Okay, the time will be the same in both the X and the Y direction. Okay, now what is given? All right. Well, let's start with U because we know the initial velocity is this way, right? What can we say about that? All right. What can we say? Do we know UX? So the question actually didn't tell us what UX is. If you rewind a little bit, right, and look at the question, it just says it's launched horizontally. So I don't actually know this. Okay, what else do I not know? Well, my aim is to find the height of this, right? So in some sense, I want to find the Y displacement. So I don't know that, nor do I know what is the X displacement it traveled in that 3 seconds. So I don't know this. And while we're at it, let's actually say this is my aim, right? UY, however, even though it's not given explicitly, now you need to, this is part of the skill of solving this problem, is you need to be able to infer it implicitly, right? So when it says it's launched horizontally, what does that mean? Does it have a Y component? No, it's purely in the X direction. So there's no Y component. So initially there's 0 Y component velocity. At the end, right, it's hitting the ground, you know, like this. So there is certain amount of velocity. So this is not going to be 0. I just don't know what it is. Okay. What else? Do I know Vx? No. I don't know what's the final velocity x direction is. Do I know AY? AY is the acceleration in this process, right? During this process, after the instant after you launch it, after you kick it, and until the moment just before it hits the ground. When it hits the ground, you will introduce an extra force, right? You will have a normal force. But just before you hit the ground and just after you kick it, when you kick it, there is an extra force. Over here, there is no force except for gravity. And gravity will introduce, so that's the free body diagram looks like that, right? You have a weight. So the net force, right? Remember MA equals to the net force. And in our case, the net force is W, is the weight. And the weight, we have a formula for that, mg, just a quick recap, right? And now you realize A is G. But the net force is in the downwards direction. In my case, it's negative Y. So this is in the downwards direction. A is equals to G in the downwards direction. So I know AY, and I need to put G in the negative Y direction, right? So AY is negative G throughout this process. There's no other net force. So the weight is the only net force in throughout the whole motion over here, okay? And do we know AX? What is the acceleration in the X direction? We don't know, or do we? We do know. Can you see what is it? Right, it's 0, right? The reason is because exactly that. This is the only force pushing it down. And the acceleration, if these guys should be vectors, right? The only net force is the downward force. So there's no horizontal forces acting on the ball throughout the whole motion, all right? So if there's no net force, there's no acceleration. So if there's no net force in the X, draw this in components, right? So you have XAXAY equals to F net X, F net Y, right? So if you have no net force, if that's 0, then it must be 0, right? So that's so that MA, you can distribute this in since it's a scalar. So M times what equals to 0? This has to be 0, okay? And yeah, you can actually put everything in, right? So this is negative mg like this, and you can solve this is negative g. You can do them all properly that way, all right? So, and finally, do you know the time? Yes, it's 3. And notice it's the same for both. So that's what we mean by having the same time for both the X and Y directions, okay? So this is our scheme, all right? So with some practice, it will just take you a minute to sort of fill in everything over here. All right, so what is our aim? Our aim is to find that. And number 3 is to pick the correct equation, pick an equation and solve. Okay, so if my aim is to do that, so maybe I should look at just the Y directions, right? And what should I find? Do I have 3 out of 5 variables? I do. I have UY, AY, and T. So I have 3 out of 5 on that side. So I will be able to find everything else over there. Okay, so what do I want is I want to pick an equation with no V. And if you look through the 4 equations, I believe now you have it in mind, right? You remember all of them by heart, right? Is this one, UT plus half AT squared. There's no V involved. But what we need to do is to put a Y everywhere except for the T's, okay? And the rest is now just plug and check. Remember, to present your work, draw a diagram. If you want, write this is optional, but it's just helpful in all these type of problems. But when you get to actually your work, write down the equation that you're going to use first before you plug in the numbers. Don't start plugging in the numbers because that's very hard to tell what equation you're using. And it's hard to give you partial credits if you plug in the wrong numbers. But if you select the right equation, at least you probably get a point over here for picking the correct equation to use. All right, so the aim is to find that. All right, we'll leave that out. That is 0. And half A is minus G. G is 9.81. So you can do that. And T is, sorry, I do know T. T is 3 squared. All right, so now you go in and plug everything in your calculator. So I think I got, so you can double check. I was approximating this. Let's see if I can do this in my head, right? Let's approximate this with 10. So minus 10 divided by 5, that's, so first of all, that's 0. That's minus, divide by 2, that's minus 5 over here. 3 squared is 9, 9 times 5 is 45. So this should be around 45, and I'll get a minus sign like this. All right, remember, check 3 things at the end. Check positive or negative. Should I reject anything? Check significant figures, and check if you have a unit. Okay. Now I got a negative sign. I got only one answer, so I don't necessarily need to reject anything, but you want to check, does it make sense? Negative, because I called my origin over here, right? So it would be better if I had drawn it over here. Then it will implicitly define the origin. Then the displacement is negative 45, right? So that makes sense because it's going downwards because my y is pointing there. Significant figures, 2 sig figs, I think that is what is given, so that's fine, and just add that and you're done. Okay, so as you can see, it looks more involved. You suddenly double the difficulty, but essentially it's the same process. All right, so this is an example where we only utilized one side, and now let's look at another one where we'll utilize both sides, and that's what we typically call projectile motions. So we'll move on to look at that.